All right, so today we're going to find out why the sky is blue. Something we might have wondered for a while, if you've ever looked up at the sky. To begin with, what we're going to do is write down some ideas why you think the sky might be blue, why you've heard the sky was blue, what people would say if you were to go to the mall and take a survey. What do you think people say if they were asked, why is the sky blue? Can you do it Family Feud style? What do you think is the most popular reason? So write that down. Once you've got your answer, take a moment to see if you and your neighbor agree. Also, if you can think of some reasons why those ideas might not be right, or some questions you might ask somebody who thought that was the reason. There's a space for that on the sheet as well. Alright, so Family Feud style. Who thinks they know the number one reason that people say the sky is blue? Oh, Lauren was picking on the dog.
Because the water reflects the ocean.
Okay, so it's a reflection of what?
The ocean.
Reflection of the ocean. And it turns out that is a very popular answer. The idea that why the sky is blue, it's a reflection of the ocean. What question would you have after you asked them that? They said, hey, why is the sky blue? Oh, it's because it's a reflection of the ocean. You would ask? Okay, tell me, you would ask what? Why is the ocean blue? You know what they would say?
It's the sky.
Reflection of the sky. There you go. So, I guess that's all there is to it. No need for a lesson. We got it all worked out. The sky is blue because it's a reflection of the ocean. The ocean is blue because it's a reflection of the sky. End of story. Or, you know, we can say that because we're in California, right? We're, 100 miles away from the ocean. But what if you're in Kansas? You've got nothing but wheat on the ground. What color is the sky? Wheat color? Okay. Turns out, they get a blue sky too. So it's not just a reflection of what's on the ground. That's not what makes the sky blue. All right, so let's get into it a little bit deeper. There is a jar of sky. We've bottled it up, we've jarred it, preserved for future generations. They can have some sky. Doesn't seem to have any color to it. By the way, what's in there? It's air. Okay, air. And where is that on our? So we've got a quick periodic table here. Where should I look to find the air?
Oxygen.
Oh. What is it mostly? Air is mostly
nitrogen.
Mostly nitrogen, and then some oxygen, and then some other stuff too, right? Isn't that what it's made out of? About 78% nitrogen. So mostly more nitrogen than anything else. Oxygen comes in second place. Others, 3% or so. All right, so that's... Now, are any of those blue or any other color? Okay, George says oxygen is green. Oh, no. Yes, those are the colors of the elements, and gold is pink. All right, so don't go by that. That's not the indicator. All right, so these are all colorless, transparent, no particular hue or shade to them. So that still leaves us with a mystery. Why is the sky blue? Well, sometimes the sky isn't blue, right? Look at the nighttime sky. Okay? Nighttime sky isn't blue at all. Mostly black, dotted with stars. So the nighttime sky is black, but in the day, oh, you know what I did a couple years ago with Mr. Hodges? Went to Paris, got this nice picture of some blue sky. Oh, and a guy jumping over the thing. So apparently in Paris, they have blue skies. And in Utah, they've got blue skies there as well. So what's one thing that seems to be important? The nighttime sky was not blue, but the daytime sky in Paris, the daytime sky in Utah, were blue. Okay? So Ricky, what do you think?
Light.
Got to have some light. And isn't it nice we've got a bright source of light called the sun? Oh yeah, the sun. All right, so the sun is our nice bright source of light. Well, let me show you one more picture. Taken in the sunlight. Oh, I didn't take that picture. But it's sunshiny, and yet the sky is black. Huh. So they've got the sunshine. What's apparently another critical ingredient for my blue sky? I must have sunshine. But what else? That isn't here. What is it? Got to have some chemical. What is it?
Atmosphere, maybe?
Got to have some atmosphere. Got to have some air, right? So let's have both. Those are both the critical ingredients for the blue sky. Got to have air. Got to have sunshine. If I don't have air, then I get that moonshot. I got a black sky. If I don't have sunshine, I've got the nighttime sky, black dotted with stars. Okay. That still leaves us with the question, why is the sky blue? We're not going to get to the answer directly. We're going to go on a little detour here. I want to tell you about tuning forks. You guys have seen tuning forks before? Mm-hmm. Not strange to you? Okay, tuning forks, you know how they work. You hit them, they vibrate, they make a sound. This one, you can hear if you're close. I can hear it. Oh, very nice. But you guys can't hear it. Okay. Well, let's make it so that you can. If we attach it to a box, when the tuning fork vibrates, the box vibrates. There's a lot of air in contact with the box. So now, we all get to hear it. Connected to the box, the sound box vibrates when the tuning fork does. Hey, is there a way, if I didn't want to listen to this for a couple seconds, is there a way I can turn it off without just waiting for it? Okay. I can do what? Oh, I can touch it? Okay, so let's try that. And then the sound goes away. Isn't that nice? Well, I've got two tuning forks. And they both play the same note, so that's kind of nice. Very warm tone. And I've got this tuning fork. Same note, right? And touch them to quiet it down. But watch what happens when we do this little trick. It's possible. You do this left-handed. Do you still hear it? I mean, I stopped it, right? Oh, but I didn't stop it. I can still hear the sound. People up close can still hear that. How come? Tell me, what's your theory? Okay, come up here. Let's see if we can prove it. Okay, so stand on the other side. And you got long arms, right? You can reach over here. Okay, so I'm gonna play this like we did before, and then I'm gonna stop this one. And then Tomek's gonna try out his theory and see if he can stop the sound completely. Okay, so you ready? Here we go. It worked. Thank you, Tomek. He was correct. He was correct. Nicely done. All right, so, but I never hit this one. How can it vibrate if I never hit it? I didn't even hit it. And it was vibrating, making sound. That seems strange. What made it have that vibration? Who's got a theory on that? Okay. Julie, what do you think?
The vibration went into the air so we could hear, but it also went into the other box and made the air inside swing, and so the metal thing swung too.
Okay, so hitting this one made sound, and we could all hear it. That was nice. Some of that sound, and I kind of cheated. I kind of directed it this way, right? That's kind of being sly. So I directed some of that sound toward this one. The vibrations, the sound, made this box vibrate and made this tuning fork vibrate without ever touching it. It was the sound that made this vibrate. Physics types refer to this idea as resonance. The vibrations of one thing set up a vibration in another thing. This was being forced at a certain frequency. Oh, and what frequency did we force this one at? Same frequency as this one, which is the same note. So this one was sending out sound waves, pulses of air pressure, that caused this one to vibrate at the same frequency, and it's happy to vibrate at the same frequency. That's its one note. So there was a resonant oscillation set up in this one, caused by this one. Now, we also refer to that if we've got some waves coming from over here, passing through this distance, and it sets up a vibration in this one, and these sound waves can now go anywhere they want to. You know, if I could focus it better, I could be very far away here, magically send the sound in here, and have this one kind of take off on its own. That process, because the light was, or the sound rather, was coming in from a particular direction and then whoosh, kind of exploding out in all directions, physics types refer to that as scattering. So that would be an example of scattering, that resonant oscillation that was set up and gets scattered out in all directions. All right. So let's take a look at the animated version. If you were in the back, maybe you didn't hear all that. So here's the same thing over again. Here's our tuning fork. Oscillates nicely in the sound box. We can all hear it. Goes on and on. Now we can quiet it down by touching it, stopping the vibrations. But if we bring in a second tuning fork and try to quiet that first one, the sound persists. Try it again. There comes my hand, and then here's Tomek. There he is right there. Okay. So yeah, what was happening was energy from the first tuning fork was coming across in the form of waves at the right frequency to set up resonance in the second tuning fork. It became a source of sound and essentially scattered the sound that started here, scattered the energy. So, that's an example of scattering. It's nice that we have these tuning forks set up with the same note, because if we hadn't had two tuning forks with the same note, maybe we had something like this. By the way, this tuning fork would play a what note? Oh, a lower note. Yeah, that's right. The sound waves would mostly just pass right through it. Okay? Unscattered. Wouldn't cause a resonance because they don't match. This isn't hearing its own tone. It's hearing a different tone. It doesn't get excited about that other tone. Same thing as if we had a small tuning fork playing a what note? A higher note. Most of those waves would pass right through, unscattered, because again, there's a mismatch. Suppose, we like to theorize every once in a while, suppose I went to Tuning Forks R Us, Tuning Fork World, everything tuning forks, and I decided I just got paid, went out and bought every tuning fork in the store, just because I thought it'd be a fun thing to do, have a tuning fork party. And so I've got big ones, small, I got every variety. I've got the whole array, the range of sizes, the range of notes. And then over on the other side, I went to a place that only had one size and bought all the ones that are from one size. Okay. Is it possible, what do you think, if I took my little tuning fork mallet and hit every tuning fork on this side, just bonked them all, would any of them on the other side start to go into oscillation?
Yeah.
Okay. So Cameron's got to figure, what do you think?
I think if you hit the one that matched the note of the other side, that all the ones on the other side would start to vibrate and scatter.
Okay. Do you think there's anything in here that would match?
Yeah.
Yeah, there's got to be, let me give you a hint. Okay. There's going to be some that match. So the ones that match, since everything is getting struck, the ones that match will cause some resonance and some scattering over on the other side. All right. Here's the deep thought. We're getting close to understanding why the sky is blue. Use your imagination. This is the sun. Well, if this is the sun, what do you suppose this stuff over here is?
Air.
That's our atmosphere. That's the air. The sun putting off what color?
White.
All the different colors, right? And our atmospheric molecules, all being pretty much the same size, are like little optical tuning forks that only play the same note. So, let's get into this more deeply. There's the sun. Gives off all kinds of light. Here's a very complex graph showing all the different colors of light given off. Here's the important point. Here's the visible spectrum. That's what we can see with our eyes. The sun is putting all different colors out from the visible spectrum. So now it's got some other stuff beyond the visible spectrum either way. But the sun does put out all the different colors in the spectrum. So that's an important point there. When those colors, that variety of colors, that cacophony of tuning forks, hits our atmospheric molecules, our molecules react differently to the different colors. So here's a nice representation. We got all the different colors. Green and yellow toward the middle, then up toward blue, violet, and ultraviolet, down toward orange, red, and infrared. All the colors of the spectrum, and then some outside of our visible spectrum. Here's a representation of an atmospheric molecule. Remember, it's oxygen in our atmosphere is not just O, it's O, O2. Same thing with nitrogen, right? Diatomic, 2 atoms. Here's some sunlight coming in. Here's a color representing ultraviolet. Now, ultraviolet we can't see with our eyes, but ultraviolet turns out to be our atmospheric molecule's favorite frequency. Its favorite wavelength, its favorite tone, if you will. It's the one that resonates, just like these two resonated. Okay. Ultraviolet is scattered better than any other color or any other part of the electromagnetic spectrum. So ultraviolet is tops. It's the king of scattering. But we can't see ultraviolet, and a lot of ultraviolet gets blocked out, we hope, by the ozone layer, right? That's not O2, it's O3, people that know. Does a pretty good job at blocking out a lot of ultraviolet, which is good for us so we don't get skin cancer as fast. What about violet, though? Violet comes in, and it's pretty close. It's not exactly ultraviolet, but look, it's pretty close. It still gets scattered very nicely, but if you look, people up close can see a little, you see this little ghost? A little ghost of some light that didn't get scattered. Instead of getting scattered, it got transmitted. So again, light from the sun, a lot of it gets scattered in the violet part of the spectrum, but a little bit of it sneaks through and gets transmitted. Okay, let's keep going. What about blue? Again, very well scattered, but a little bit more transmitted. Green. Let's do green. We're starting to get fade a little bit on our amount scattered, and we're really getting stronger on the part that's transmitted. Yellow. Can you see how this is getting a little bit weaker? This is getting a little bit stronger every time. Let's go to orange. Oh, look at that. Orange mostly comes through. Doesn't get very well scattered. Red. Mostly transmitted. Hardly scattered at all. Same thing with the infrared, below the red. So, mostly transmitted, very little scattered. So the extent to which the light gets scattered depends on how close it is to those optical tuning forks' favorite frequency. And that favorite frequency is ultraviolet. So, here's the other factor, though. If scattering were the only consideration, we would look up and see a what color sky. What was the best color scattered in the atmosphere?
Ultraviolet.
Ultraviolet we can't see. What's the color that we can see? Okay, did you guys appreciate the, when you were out at lunch, did you look up and see the violet sky? Okay. It wasn't violet. But violet is the color best scattered in the atmosphere. Well, we don't see with a computer or a CCD or a sensor. We see with our eyes. And it turns out our eyes have different sensitivities to different colors. So you look. Okay, who remembers cones and rods? Anybody remember that? I had biology a long time ago. Okay, who remembers which ones are good for color vision? Which ones give us the color? Anybody remember that one? Nobody's willing to... Okay. Let's see, Michaela, what is it?
I think it's cones, isn't it?
It is the cones. Okay. So the cones are good for the color. The rods are good for the light sensitivity. So if we put both of these little sensitivity charts, here's the relative sensitivity, here's the wavelength. If we put those together, we get something that, if you simplify it a lot, basically looks like this. We're not terribly sensitive to the violet, and we're not terribly sensitive to the red. Our sensitivity goes up toward the middle of the spectrum. In this area, sort of in the yellow-green portion of the spectrum, that's where our eyes are most sensitive. And you know about that color that we're most sensitive to, right? Okay? You've seen this color before, especially if you play tennis. Okay? What's the fancy name for this sort of lime green? So that starts with a...
Chartreuse.
What is it?
Chartreuse.
Chartreuse. Oh, like your shirt. Look at that. A couple people wearing the chartreuse. All right, so they can be seen from outer space because of the chartreuse. All right, so if you're into tennis, some municipalities, some cities, make their fire trucks this chartreuse, this lime, yellow-green kind of, for visibility reasons. Why not make the fire truck the most visible color? If you're really into tennis, you should probably get some tennis shoes. Okay. And when you're done with the tough tennis match, you want to go home and relax a little bit. Okay. Have some nice furniture. Wouldn't that be nice? Who has, anybody have this? No. See? Maddie's got that. It's nice to relax. You put your tennis shoes up on the little tennis arm in there. Okay. Very nice. All right, so that leaves us with a question. A couple questions. Our eyes are more sensitive to green than they are to blue, but we look out and we don't see a green sky. Has anybody put the ideas together yet to know why we don't look up to see, a beautiful chartreuse sky? So, George, what do you think?
Is it because it does violet more and we're sensitive to green?
When you say it does violet, what does?
Well, it scatters it more.
Okay, who does?
The optical things that you're talking about.
Okay. And where are they?
In the atmosphere.
Oh, yeah. So the atmospheric molecules, right?
Yeah.
So the atmospheric molecules scatter, what do they like to scatter?
They scatter violet.
Yeah, they like to scatter the violet. So they scatter violet best. Green, kind of far down the list, right? Maybe a little bit too far. So it goes from violet to the blue to the green to the yellow. And by the time we're getting toward where our eyes are most sensitive, we're really kind of down the scattering. So the color that our eye is most sensitive to isn't scattered very well in the atmosphere. So we don't see it when we look up. So you say, it's all about the scattering. Let's go back to this idea. Then we should have a violet sky. Okay? Violet is scattered better than anything else, and yet we get a blue sky. So why a blue sky when violet is the champion of what got scattered? Okay, so
because not a lot of violet light passes through the molecules.
There's a limit on how much violet light gets in. It might be blocked out by other things, and then there's one other factor. Kind of important word. What is it?
Is it that like the violet, like in sky, and like the green that like sticks out to us? Do they like mix or something?
Well, it's not that they mix. It's just that what do we remember about our eyes? Okay.
Our eyes are like less sensitive to the violet than they are to the blue.
Okay. Violet was way down on the list of what our eyes are sensitive to. We're very sensitive to that chartreuse, but it falls off dramatically as we look to violet. So violet is scattered very nicely, but our eyes are not sensitive to the violet. If our eyes were as sensitive to violet as they are to all other colors and everything was equal, then the sky would appear violet to us. The fact that it doesn't appear violet is an indication that our eyes have a sensitivity curve that's different from being flat. All right, so those are the two things going on. So blue is really the what?
Happy medium.
Okay, sort of the happy medium, the compromise, right? It's a compromise between the sensitivity of our eyes, which is in the green, the chartreuse, and the scattering of light, which is predominant in the violet. So think about what color is between those two, right, on the spectrum. The blue is. Okay, so blue is between the green and the violet, and we see a blue sky. It's the compromise. So it's not really easy to answer why the sky is blue in just one quick answer. It's a couple things going on. It's what's scattered in the atmosphere, and it's what our eyes are sensitive to. Right? So, okay, so we are pretty well understood? Yes?
Does that mean like the sky appears other colors to like animals and stuff?
So yeah, what about that? If you got a different animal, maybe has a different sensitivity range, a different curve than ours. Like ours peaked at the green. What if it peaked at violet and could see ultraviolet? There are some animals that can see in the ultraviolet, isn't that right? Their sky would be whatever ultraviolet looks like to them, I think. So yeah, it depends on the species, right? So different animals might see a different color sky based on what their sensitivities are. But so there's two parts of it, right? There's the scattering in the atmosphere and there's the sensitivity part. So those come together for us to make a blue sky. They might come together for something else to make a different color. But yeah, all that's possible, yes. Good question. All right, so let's, oh yeah, now we got a thing to do. Let's do our thing. Here's what we're going to do. I need question.
When people are colorblind, what colors can't they see?
You know, there's different kinds of color blindness, and for some of them, blue might be a color that they're not sensitive to. So you say, oh, what's their sky? It's usually, I think, from what I've heard, gray. Just kind of a pale gray is what it looks like to them. And they wouldn't be able to distinguish. If you put some pale gray in the blue, it's the same color. They wouldn't be able to distinguish that. But yeah, there's different kinds of color blindness and different spectrums of sensitivity or lack of sensitivity. So it depends on the person. All right, so here's the thing that we're going to do. Each group is going to get a little skinny fish tank, okay, which are in the back, and they have letters on them. And so one person's going to get that and fill it up halfway with water. We've got 3 convenient filling stations, back, middle, and front. Somebody else is going to get the group's flashlight, which has a letter on it, and a stirring rod, which doesn't have any letters on it. Okay, can we handle this? So, go get your stuff. Paper towel conveniently located everywhere in the room, yes? Okay, it's not, none of them leak, but when you fill the water, sometimes the water goes to different places. Okay, I'm going to put some mop and glow into your tank. We're going to simulate the atmosphere. But we don't have enough room to actually do the atmosphere, so we're going to kind of concentrate the atmosphere into these tanks. Mop and glow. So you put it down on your floor, you mop the floor, and then your floor glows. Good. Halfway full, so you wouldn't spill on the way down.
Oh my gosh.
Okay, stir it. Okay, somebody get the stirring, somebody get the paper towels. Do this on the back table so nobody can see. Sit down so we're not blocking the view.
You're in my way. It's okay.
Okay, this is the mop and glow.
B, what do you guys have? I don't think anyone grabbed
You're going
it.
to stir gently, yes? Stir gently. Okay, oh, there's more over here.
On the far end, I was like, oh wait, I want to see it.
I know.
Sounds so excited. You ready to do that?
Okay, who didn't get mop and glow yet? Everybody's got mop and glow. Stirring gently as to not cause too many bubbles. Everybody's got mop and glow? Okay, I wouldn't drink mop and glow, you know. I wouldn't drink pine salt. A lot of people that wouldn't drink.
Wait, so Mr. Baird, so if it was like a dog lunch instead of mop and glow,
I don't see anything. What's mop?
Not necessarily. It could be, but most things will be this kind of Okay, so you guys can see the instructions on what to observe, yes? So please make your observations. Okay, everybody drop the lights a little bit. Okay, so what color do you see? Whoops, hang on. It's very exciting, I know. I can hardly contain myself. Alright, so what color do you see closest to the source of light? It tends to be a little bit bluish, right? Do you see my really bright one up here? I've got like a super bright LED flashlight. So a little bit bluish, close to where the light source is, right? And do you see how the colors kind of change as you go across? And when you look from the far end, looking back toward the light source, did you try that yet?
it's red.
It's kind of red, isn't it?
Real red.
Okay, it's a surprisingly deep red, yes?
That's easy red.
Okay, let's get the lights back up.
A is like blue.
Okay, now, I think we might have answered another question that we didn't even think to ask yet. Is blue the only color you ever see up in the sky? Oh. So Riley, what? When the sun sets or the sun rises. Okay. We've even got some pictures up here. Looks like there is one of a sunrise. See how orange the sky is? So we can get some reds and oranges up in the sky as well, can't we?
Yeah.
Do you now see how that can happen? Let's go through it here. First, let's go through what you saw. Okay, here's a quick rendition on what you saw. We put the water into the tank, very nice. Got the water sound. You turn the light on, and you see it's bluer at this end, oranger at this end. If you look down from above, it's even a little bit more concentrated. And when you look down from the end, yours might even be deeper. You know, mine was kind of orange. Yours might have been even a deeper red, and how much mopping glow put in. But let's think about this. Let's think about how that sky gets orange at sunrise and sunset. First of all, let's zoom in here. Daytime sky. Noontime, the sun is as high up above us as it's going to be. The colors from the sun that get through to us are the oranges, reds, and yellows, because the blues and the violets and the greens get scattered out at various distances. So if you were to look directly at the sun, which, by the way, is a good idea or a bad idea? Really bad idea. If you want to be able to see tomorrow, don't look at the sun today. All right, so it would have a bit of a yellow look to it, partly because the other colors got scattered away. But that's not what we see when we see a blue sky. We're not looking at the sun when we're seeing a blue sky, right? We're looking at the sky around the sun. Okay, so let's look at what happens to the sky around the sun. Here comes the sunshine, hits the atmosphere, look what it does. All those little optical tuning forks scattering the blue away from themselves. Scattering blue. Now, they scatter the other colors as well, but remember, blue was the compromise between our sensitivity and what got scattered. So blue's coming at us from all these angles. Wherever there's an atmospheric molecule, which is pretty much everywhere in the atmosphere, blue is coming at us. Okay, so we got blue coming at us from all those different angles. Well, the blue that makes it through to us is robbed then from somebody else where it's sunrise or sunset. So let's take a look. Can you see that if you're at sunrise or sunset, which is, by the way, where is this on your sheet? A, C, B, where is it? A. Is it sunrise for them?
Yes.
Sunrise, right. So, can you see that it's a thicker layer of atmosphere that the sun has gone through to get to the person at A? So the blue's been scattered away, the violet's been scattered away, the green's been scattered away, the yellow's been scattered away, even some of the orange has been scattered away. All that's left is the oranges and reds. It's the same thing that gives us the daytime blue sky, that gives us the sunrise and sunset orange skies and red skies. That blue, that's part of our blue sky right now. The person for whom right now is enjoying sunrise or sunset isn't getting that blue because it's part of our blue sky. It got scattered away from them. What do they get? The color that didn't get scattered very well. The reds, the oranges. Okay? So, same mechanism that makes our daytime sky blue makes our sunrise and sunset sky orange or red. Okay? Questions? All right, it's a lot of information to take in one quick setting. All right, so we'll talk more about this in the future, but for now, if we could, s'il vous plaît, get the flashlights where the flashlights go, get the tanks where they go, carefully, without spillage.
It's not that bad.